10. Before the Big Bang. The answers to the question of the Big Bang and how the universe came about are like matryoshka. Because, as in black holes, the concept of singularity puts information into a paradox. That's why there is no such thing as time before the Big Bang. The start is Bin Bang. Time and space begin here. But some theories are good enough to be true. For example, if we consider the current space is expanding. If this expansion continues, there are two possible situations. Either the universe will continue to expand and cool, or gravity will take over again and the universe will shrink again. That's why scientists say that there is actually a cycle in the universe. The universe expands and then shrinks again. The other theory, a scientist who received the Nobel Prize in 2020 said, the cold state of the universe can cause the hot and dense state, and vice versa can cause cold condition and hot and intense condition. But time is different for both. Another theory says that we are actually inside a black hole. But if we look back at our current knowledge of black holes convert matter into radiation and vaporize it. Finally, it evaporates. If Big Bang is a black hole, why didn't it evaporate? Or why did gravity weaken to dark energy when it was so dense? Unfortunately, there is no answer to these questions because we do not know the relationship between both dark energy and the fundamental forces of such intensity. Scientists say we need a new quantum theory to know this. Others say that the light that provides us with information about the universe still does not come from the deeper points of space. We learned something about before the Big Bang. Let's get back to this again. How did the first atom or quark come about? 9. How did matter come from nothing? Quantum field theory tells us that even a vacuum supposed to correspond to empty space-time is filled with physical activity in the form of energy fluctuation. These fluctuations can cause particles to fly out and disappear after a short time. This may sound more like a mathematical quirk than real physics, but such particles have been detected in countless experiments. The space-time vacuum state is apparently teeming with particles that are constantly being created and destroyed out of nothing. But perhaps what all this really tells us is that the quantum vacuum, despite its name, is more than nothing. Considering that we can only see 4% of the universe, it is not unreasonable, because dark energy and dark matter may be the cause of this atom and quark formation. Maybe it's actually normal for quantum physics to make something out of nothing. The knowledge of how the first quark was formed is therefore a mystery. But we know how atoms were formed after the Big Bang. The fireball from the Big Bang was so hot and dense that it's called quadrillion temperatures. It was too hot to form atoms, but the universe began to expand and cool. This cooling allowed the particles to form clusters of nuclei, resulting in most of the universe's helium isotopes and small amounts of the hydrogen isotopes deuterium-2H, as well as very small amounts of another isotope, lithium-7. Other elements formed inside stars. 8. Space has exceeded the speed of light. But this is against Einstein's principles. But it's not because space is outside of it. So what caused this expansion called inflation? We don't know exactly why. But current theory says that the inflation field is causing this expansion. During inflation, the inflation field made a rapid transition from a high energy state to a lower energy state. This transition caused the universe to expand exponentially, causing the universe to grow incredibly fast in a very short time. This expansion would have stretched the fabric of space and smoothed out the irregularities, providing an explanation for the observed uniformity of cosmic microwave background radiation and the large-scale structure of the universe. 7. Is the universe flat? The answer to this question is yes, the universe may be flat. So how do we know? We know from the cosmic microwave background radiation, which is perhaps the most important proof of the Big Bang theory. The cosmic microwave background radiation released in the early moments of the universe carries important information about the past states of the universe. By studying the temperature fluctuations of the CMB, we can understand the geometry of the universe on a large scale. The observations show that the anisotropies, temperature fluctuations in the CMB are distributed as predicted by a flat universe. But don't think of it as a 2D flat, of course. There is a good example on how to flatten at astronomy.com. I didn't add it because it is complicated to explain and the video will be long. But you can find it in the description section. 6. The cosmic microwave background radiation was accidentally discovered. In 1964, Arno Penzias and Robert Wilson, working at Bell Laboratory in New Jersey, began to study microwave radiation from the universe using radio antennas. However, they noticed that their radio receiver was picking up a constant noise. They climbed the antenna and saw a pigeonhole. They even killed the pigeons, but the noise still continued. Penzias and Wilson conducted several tests to understand the reason for this constant noise in their antennas. Later, they realized that this noise did not come from any local source, but from all directions in the sky. This aroused great interest, especially for scientists working in the field of radio astronomy. Arno Penzias and Robert Wilson contacted theoretical physicist Robert Dicke at Princeton University. Dicke suggested that the light released during the dense and hot period of the universe's youth could be traced back to the present-day CMB by cooling. This helped Penzias and Wilson understand their discovery. This discovery by Penzias and Wilson strengthened the Big Bang theory by providing evidence of the hot and dense period in the universe's youth. This discovery was regarded as critical evidence bearing the traces of the beginning of the universe and contributing to the understanding of the early moments of the universe. 5. So what created the cosmic microwave background radiation? As the universe expanded and cooled, it reached a point where the temperature was lower than the energy required for more particle-antiparticle formation and destruction. As a result of these interactions, electrons and positrons disappeared and photons were released. About 380,000 years after the Big Bang, the universe cooled enough for electrons to be captured by atomic nuclei and form neutral atoms. This phenomenon is known as recombination. The universe, which was previously opaque due to photons scattered by free electrons, became transparent when these electrons combined with protons to form neutral hydrogen. With the universe becoming transparent, photons previously continuously scattered by electrons were able to freely circulate in space unhindered. These photons formed the primordial light that has filled the universe to this day. In the billions of years that have passed since the Big Bang, the expansion of the universe has caused these photons to cool considerably, resulting in the CMB's microwave radiation with an average temperature of about 2.7 Kelvin today, or minus 454.81 degrees Celsius, led to observation. 4. Matter-antimatter contradiction. According to the Big Bang theory, the same amount of matter and antimatter should have formed at the beginning of the universe. But in the universe we observe today, matter is much more dominant than antimatter and almost alone. This phenomenon is called matter-antimatter asymmetry, and is a great mystery to cosmology and elementary particle physicists. Matter and antimatter are two types of fundamental particles with exactly equal but opposite charges. For each matter particle there is a corresponding antimatter particle. When matter and antimatter particles combine, they transform completely into energy and perform annihilation. This phenomenon is called matter-antimatter asymmetry, and is a great mystery to cosmology and elementary particle physicists. Several explanations have been suggested. CP violation. 1. CP symmetry means that the properties of a particle are the same and the particle-antiparticle pair is equal to each other. However, in some particle decays, the CP symmetry is violated. This violation may be a mechanism for the conversion of matter to antimatter. 2. Hiding CP violation. It can be considered that CP symmetry is violated but not effective at low energies. That is, although CP violation occurred in the early universe and the conversion of matter to antimatter took place, this effect may not be seen in low energy conditions. 3. Baryon asymmetry. The reason for the asymmetry between matter and antimatter in the universe can be associated with processes called baryon asymmetry. Baryons make up matter, while antibaryons make up antimatter. If slightly more of the baryons were produced, this could cause matter to dominate over antimatter. 4. Heavy quarks and leptons. Some processes in elementary particle physics can lead to the conversion of matter into antimatter. Especially the interactions between heavy quarks and leptons can be important in this regard. 5. High-energy physics. High-energy particle accelerators such as the Large Hadron Collider can perform potentially important experiments to understand the cause of matter-antimatter asymmetry. This topic is still an active area of research, and the cause of the matter-antimatter asymmetry has yet to be fully explained. However, studies to solve this mystery continue with particle physics experiments and cosmological observations. In the Big Bang, it is believed that the four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear force, could be one force when the universe was one. This theory proposes that the four fundamental forces are actually faces of the same fundamental force in different directions in high-energy conditions. The different fundamental forces diverge as the universe cools and expands. That is, as the universe cools and expands, the forces diverge. This theory also gives insight into dark matter and black holes. In this theory, we think all the forces converge because remember Einstein's formula E equals mc2. This shows that they can transform into each other. 2. One day the stars and galaxies will disappear. The expansion of the universe has been going on since the Big Bang, but for a long time the expansion slowed down. About 5 billion years ago, the expansion of the universe began to accelerate again. This means that galaxies are moving away from each other faster. The accelerating expansion of distant galaxies was first observed by looking at distant galaxies in the late 1990s. Studying the luminosity and spectral properties of supernova explosions revealed the accelerating expansion of the universe. Galaxies were redshifting, meaning they were accelerating further away. This acceleration is thought to be caused by dark energy. If dark energy persists, it is predicted that the rate of expansion of the universe may continue to increase. This means that in the future it will become more difficult to reach other galaxies, and galaxies may become isolated. And this means that if their expansion rate exceeds the speed of light, they will disappear completely. 1. The end of the universe. Current observations and the expansion of the universe show us two possible situations. Either the universe will expand and cool, or the power of dark energy will run out and gravity will shrink space again. Maybe there will be a new Big Bang after this shrinkage. Other important theories are as follows. Finite space theory. Increasing the rate of expansion can accelerate the universe to reach a finite size. If expansion is constantly accelerating, it may be possible for the universe to reach a growth limit where it has a finite volume. Heat death. Due to the law of entropy, energy slowly becomes disordered and eventually all systems remain in disequilibrium. This means that a heat death will occur in the universe. All energy is exhausted and there is no energy left to do any work. The Great Rip. If dark energy increases rapidly, the expansion rate of the universe may increase as well. In this case, first the galaxies, then the stars, and finally even the atoms cannot resist gravity and the universe falls apart. This scenario predicts that the end of the universe will happen quite dramatically and quickly. Characteristic time. Some theories suggest that the end of the universe will be neither cooling nor compression, but will occur at a characteristic time interval. This scenario says that the end of the universe will occur according to a certain time scale. Multiverse theories suggest that the universe is not just our own observable universe. These theories claim the existence of different universes or cosmos, and even certain universes may have different physical laws. Bonus. I wanted to put this as a bonus as this is something that is covered in most videos. There is no explosion in the Big Bang. If there were, then maybe we would say Big Explosion. In fact, when the name Big Bang was first introduced, scientists were making fun of it, but its use in the media has given it popularity under that name. If not blast, then what? This is an expansion that started all over the universe at the same time. The Big Bang can be a beginning, an end, or both. We still know very little about space and how physics works in space, especially dark energy. Dark matter and quantum physics will probably teach us a lot. Imagine that everything we understood was actually 4% of the universe. So what happened to dark matter in the Big Bang? Forced to interact with normal matter, or was it outside of the Big Bang? We have come to the end of another video. You can support the channel by subscribing and liking the videos. Thanks for watching. Bye.